Okay, good morning, everyone. Let's get started. In the last few classes, we saw various techniques for proving achievability and converse results in information theory, and we also applied some of these and discussed in some detail the point-to-point channel coding problem. All right. So from this class onwards, we'll move on to multi-terminal problems, but there are more than two users. There's more than one transmitter and one receiver, or for example, even in the case of the compression problem, you can think of it as a problem of communication, but except over a noiseless channel. So there's still a transmitter and a receiver. There's someone who's encoding, who's compressing, and there's someone else who's decompressing. So now let's see what happens when there are either multiple senders or multiple receivers. How does the problem change? How does it get? Is it more complicated? And how do you generally deal with situations of this form? So the problem that we are going to start with in this class is what is called the distributed source coding problem. And we'll mostly look at lossless compression. But maybe on the way I'll also indicate what happens in the case of lossy compression. Okay, so the problem is as follows. So we know what to do if we want to compress a single source. Let us say that we have a file, maybe it's a text file or an audio or a video file, and our goal is to compress it losslessly. So standard English text file has a lot of redundancy, but you can compress it using zip or 7-zip or gzip, any compression format you choose, such that it occupies less space. And if you want to recover the original file, then there's some way of recovering it from the compressed file. Right? But now let us suppose that you have two senders and who have files of their own. So you have sender 1 who has, let's say, xn, and sender 2 who has yn. So one way to think about this is, let us say that you have two sensors which are placed on the field and they're making some measurements. Let's say that they're making, say, temperature measurements. Right? So these temperature measurements, of course, if the sensors are placed not too far apart, then the temperature measurements are not going to be too different. They're going to be different from each other, depending on how far apart the sensors are placed, but they won't be exactly the same. They could be maybe spaced far apart so that the temperature is different, and also maybe the devices that you're using are also have their own characteristics. So there's a little bit of internal noise or whatever. Right? So certainly the measurements are not going to be identical, but they're going to be related to each other, because after all, you are measuring the temperature in some certain geographical area. So these measurements are going to be correlated with respect to each other. Okay, and let us say that you want to send these measurements to some fusion center or some central server. Okay, and assume that the channel from the sensors to the server or the fusion center, these are noiseless. Okay, but although they're noiseless, you want to minimize the number of bits that is sent. So let us say that you have let's call it sensor 1 is making, say, n measurements, and it wants to send these n measurements to the server. Sensor 2 is also making n measurements at the same time, and is sending and has to send these n measurements to a server. And you want to minimize the number of bits that are communicated from the sensors to the server. So let us say that sensor 1 somehow encodes the measurements it has, and let us say that so these n measurements are compressed to kn bits, and these are transmitted to the decoder. So this comes from 0, 1 to the kn, Similarly, sensor 2 compresses its n measurements to, let us say, ln bits. Okay, and this is sent to the server. The server gets these bits together, so it gets to see a total of kn plus ln bits, and from this has to recover both xn and yn. Okay, so that is the problem, and so that's broadly speaking what the problem is. Our goal is to somehow design uh, algorithms such that uh, kn plus ln is as small as possible. So kn is also as small as possible, and ln is also as small as possible. Okay. So is the problem setup clear, or are there any questions? So, okay. So now suppose that encoder 1 decided to independently compress xn. So the assumption on xn and yn will be that xn and yn are IID. So you have x1, x2 up to xn. You also have y1, y2 up to yn. So in some sense, you can think of x1 and y1 being measurements taken at different locations. So these are spatially apart. And you can assume that x1, x2 up to xn are taken maybe across time. Okay, so this could be sort of a temporal dimension versus this could be a spatial dimension or whatever. That's one way to think about it. But depending on the context, depending on the actual problem, the physical problem at hand, these could mean different things. But our assumption will be that for each time instant t or t each I, xi, comma yi, these are distributed according to some known distribution pxy, whereas across time, so they are all independent. So xi yi is going to be independent of xj yj, where I is not equal to j. Okay, so all the components, the n components are all independent and they're identically distributed, but each xi yi are correlated with respect to each other. Okay, so that is going to be the assumption. And our goal is to understand how small we can make kn and ln. So we'll permit a small probability of error. We don't want, so for a given n, we will fix kn and ln, but we relax the recovery constraint, saying that you can make some small error. So the probability that the estimate xn hat yn hat is not equal to xn yn, this can be small. It need not be exactly equal to 0, but it is something very, very small. So typically we will want this to be vanishing in n, at least 1 over some polynomial in n. Okay, and in fact, we'll see that we can even achieve some probability of error, which is less than or equal to 2 to the minus some constant times n. So it can be made exponentially decaying in n. Okay, and we'll assume that R1 and R2 are the asymptotic rate. So we're really interested in the case where n is very, very large. Okay, and our goal is to understand, so given this particular constraint that the probability of error must be vanishing in n, how small can R1 and R2 be? Okay, that is really what we want to understand. So let us see what is possible and what is not. So to understand this, let's draw the following what we call rate region. So along the x and y axis, I'll have R1 and R2. And so this specifies a region in space, and I want to know what all rates R1, R2 are achievable. So we say that a rate pair R1, R2 is achievable, R2 is achievable for the distributed lossless source coding problem for the source pxy if we can construct encoders and decoders. If so, for every epsilon positive, we have a sequence of encoders and decoders. Such that, well, first of all, you want to be able to get close to these rates. So kn by n tends to infinity. Kn by n is less than or equal to R1 plus epsilon limit as n tends to infinity. Ln by n is less than or equal to R2 plus epsilon, and n tends to infinity. The probability of error should be asymptotically equal to 0. Okay, so these are the requirements. Okay, and we'll say that a rate pair is achievable if this happens. Okay, and we want to know what rate pairs are achievable. So what region in this R1, R2 space can we actually construct encoders and decoders? Okay, so let us suppose that we compressed xn and yn separately. Okay, suppose we optimally compressed xn, optimally compressed yn. Then what can we achieve? What rates do you think are achievable? So use the optimal compressor for xn and use the optimal compressor for yn. Then what rates are achievable?
Convex combination of R1 and R2.
Sorry, your voice is not. I can't hear what you say.
Sir, like convex combination of R1 and
Sorry?
He's saying convex combination of R1 and R2.
No, so the question is what R1 and R2 are achievable, right? In terms of PXY. So you know, so both, you know PX, you know PY, you know what PXY is. The question is how small can you make R1 and R2? Suppose I compressed xn optimally, then what is the minimum rate that I can achieve? Suppose I compressed xn independently of yn and yn independently.
like that is the entropy, the joint entropy.
So then I can compress R1 to what? H of x. So any R1 greater than or equal to H of x is achievable, and R2 greater than or equal to H of y is achievable, right? So what is this? What does this region look like?
Is it a pentagonal structure like
Is it a what?
like pentagonal structure like if
No,
R
this.
is oh,
What
this,
is this going to look like?
this is a square.
I really can't hear what you're saying.
I'm writing in the chat.
Sure. Okay, it's going to be a rectangular region. So what does it look like? What does each of these regions look like? What is R1 greater than or equal to H of x? What kind of a region is this? Any of the others? So R1 equal to H of x, what does that look like?
So that will be a straight line somewhere R1 is
A straight line which is perpendicular,
Perpendicular.
which is what? Perpendicular, parallel? What
That
is the
will be a-
slope?
that will be a value of H of x. This is, and above that one, that region belongs to R1.
Correct.
So that will be perpendicular to R1.
So this will be perpendicular to R.
R.
So it will be perpendicular to the R1 axis, so it will look something like this.
Yes, sir. And for HY, this is some value.
So this is
On
going
R2.
to be on R2.
And then
Okay.
both condition is satisfy, means
Huh.
outer part of that, which is satisfy for the both conditions.
So it's going to be this
That will be the
region over here.
Yes, sir.
Yes. So let's say R2 is H of y. This is R2 equal to H of y. This is R1 equal to H of x. Right? So suppose that we decided to compress them separately, then we know that any region to the right of this is achievable. So this general area is achievable. So any R1, R2 which lies in this, for any R1, R2 lying in this region, it is possible to construct encoders and decoders. And that follows directly from the standard source coding problem by compressing xn and yn separately. So the question is, can we do any better than this? Okay, is it possible to design compressors for which you can do much better than this region? Okay, is something in this region achievable? Okay, so to do this, let's look at the following thing. So suppose that somehow, so here's the problem, right? You have xn, which is encoded by the first encoder, yn is encoded by the second encoder, and this is jointly decoded by the receiver. Okay, so suppose that magically somehow there was one single encoder which was encoding both xn and yn. Okay, so there was an encoder which could see xn, which which could encode xn given knowledge of yn, and encoder 2 could encode yn given knowledge of xn. Okay, and let us suppose that instead of transmitting n r1 bits and n r2 bits, you just merged these two sources. So you merged these sources and you had to design an encoder, right? And you basically transmit n times r1 plus r2 bits, and the decoder just decompresses this. Okay, so how small can n times r1 plus r2 be?
Sorry, the h1 x plus h2 by h1 y. Oh, sorry, hx plus h1. R1
Should
plus
it be that small? You know that xn and yn are correlated, right?
Okay.
So there's one encoder which observes both xn and yn and is compressing it to give one code word of length n times r1 plus r2. So how small can r1 plus r2 be made? Sure. This is joint entropy of x comma y, right? So you can make r1 plus r2 arbitrarily close to h of x comma y. You just think of this as, so you have x1, x2 up to xn, y1, y2 up to yn. You can consider this as one symbol, x1, y1 as one symbol, x2, y2 as another symbol, so on xn, yn as a single symbol, right? So if you call zi to be the pair xi, yi, you know that h of z is achievable, which implies that h of x comma y is achievable. All right. So if you were somehow allowed to merge these two sources, then r1 plus r2 greater than or equal to h of x comma y would have been achievable. All right. Now, in doing so, if you are merging the two sources, then it becomes a more powerful source, right? Because after all, when you in the actual problem that we are dealing with, the encoder 1 has to compress xn without knowledge of yn. The encoder 1 knows px comma y, but it does not know the actual realization of yn. Just similarly, encoder 2 knows yn and it knows px comma y, but it does not know what is the actual realization of xn. Right? So merging the two sources only makes things more powerful. So certainly, if you were allowed to merge the two sources, then r1 plus r2 greater than or equal to h of x comma y would have been achievable. All right. So that is certainly the case. R1 plus R2 greater than or equal to h of x comma y. Okay. But you also know that, of course, R1. So if this is something that you did, okay. So what does R1 plus R2 greater than or equal to h of x comma y look like on the R1 R2 axis. So you have R1 plus R2 greater than or equal to h of x comma y.
So sir, it will be a straight line.
Okay.
Like, and
What
the
will be the
outside
slope?
region of straight line. It's like outside region of the straight line.
What will be the slope of the straight line?
That will be hx comma y. Like the intercept of x
Sir,
and y.
that line passing through hx and hy
Right.
and above that.
So will it lie here or will it lie here?
Sir, one point like hx and hy means line inside the rectangle from there to there, and that above that one.
Here you're saying?
No, sir.
Here.
This will pass through the
So the
that
intersect
axis.
in R1 axis will be h of.
Okay. So okay.
Sir, like
Yeah.
that when we are taking R1, we are not considering R2. So if R2 is 0, then that line passes through h of x, and then R1 is 0, then we consider that will pass through hy, and that above that line will that region, we have that region.
Okay.
I believe.
So let's be careful over here. So we have R1 plus, okay, so let's look at R1 plus R2 equal to h of x comma y, right? The line which is defined by R1 plus R2 equal to h of x comma y. So when R2 equal to 0, what will R1 be? So R2 is equal to 0. Where will R1 be? It will be less than hy or greater than hy.
Less than.
Uh, so I'm setting R2. So R2 equal to 0, and you know that R1 plus R2 equal to h of x comma y. So if I set R2 equal to 0, then will R1 be greater than h of x comma y, or R1 will be less?
Greater than.
Greater than.
It will be greater than h of y, right? So it will be somewhere over here, let us say. So similarly, if I set R1 to be equal to 0, sorry, this will be R1 equal to 0. And so when I set R2 to be equal to 0, so R1 will be greater than h of x, right? So it will be somewhere over here. Let's see. So really R1 plus R2 equal to h of x comma y will be the line joining these 2 points. Okay, so this R1 plus R2 greater than or equal to h of x comma y will in some sense be to the right, will be this big region to the right of this. Okay, so certainly this suggests that we may be able to do something better than this. We may be able to achieve something in this region, but that is still yet to be determined. So now suppose that the encoder, suppose encoder 1 actually had access to yn. Okay, it had to encode xn, but it somehow got side information about, so suppose that encoder 1 could compress xn by knowing yn. Okay, it somehow got this side information about yn, but so this is extra knowledge. So we'll assume that some genie gives you yn. So there is some genie which is telling encoder 1, hey, this is yn. Now you can compress xn based on this. Okay, so then what would you guess? How small do you think R1 could be made? So it still has to compress xn, but it can do so with the side information about yn. And the decoder is anyway decoding both xn and yn together. So if your only goal was to compress xn, okay, so now given yn, what is the distribution of xn? It is px given y. Px given y of whatever, given yi. Xi given yi. So this is going to be the distribution of each xi. All right. So how small do you think R1 can be made? Suppose you wanted to compress this. I don't want a formal like proof or anything, but what do you guess? How small do you think R1 can be made? So is the question clear? So we're looking at this problem, right? So you have encoder 1, let me call it encoder prime 1. It has to compress xn. Let us say that yn is given as side information. Xn and yn are jointly distributed according to pxy. And so it compresses xn to C1, let's say NR1, and then this is decompressed at the decoder to give an xn hat, and the decoder also knows what yn is. So this side information is given to both the encoder and the decoder. So if this had to be done, so if you had this problem and your goal was to design a compressor, then how small do you think you can make R1? Correct. So it's the conditional entropy, right? So it is, so R1, so any R1 greater than, so R1, you could make this as small as h of x given y. Right. So similarly, if xn were given as side information to the decoder or to the second encoder, then you could make R2 to be close to h of x h of y given x. Right. So you have h of y given x and h of x given y. If you had to draw this in this figure over here, then it would look something like this. So this is h of y given x. This would be h of x given y, and this is basically R1 plus R2 equal to h of x comma 1. Correct. So you definitely know that. So now, right now, how do we obtain these three lines? We obtained these three lines assuming that encoder 1 had information about yn, both xn and yn, and encoder 2 had information about both xn and yn. But that is not really true, right? It is certainly so really in our problem, encoder 1 does not know what yn is, encoder 2 does not know what xn is. Right, so definitely any rate below this cannot be achieved. No matter what you do, nothing to the left of this is achievable. Right? Do you all agree? So even if you make the encoders more powerful by giving them information about each other, so about the other source, even then you cannot achieve any rate below h of y given x. So you cannot make R2 anything below h of y given x. You cannot make R1 anything below h of x given y. And certainly R1 plus R2 cannot be less than h of x comma y. Right? Because these correspond to more powerful sources or more powerful encoders. And even when you make the encoders more powerful, you cannot achieve any rate below this. So the red region is not achievable. So no point in this red region can be achieved. You cannot design encoders and decoders which achieve any point in this particular region. Okay, is that clear? So we know that every point in the green region is achievable. That comes just by standard source coding. So any point in the red region is not achievable because that again comes from standard source coding, the converse to the standard source coding problem, but with more powerful encoders and decoders, right? So clearly the red region is not achievable, the green region is achievable, but there is this empty region in between where we don't know whether this is achievable or not. And in fact, we will show that every point in this blank region is achievable. So in fact, the optimal rate region turns out to be everything to the right of these green lines. So we will show that this entire region is achievable. So, which is rather surprising, right? So even though, so you have two separate encoders, you are compressing xn and yn separately. Encoder 2 does not know xn, encoder 1 does not know yn. All you know is only pxy, the joint distribution. And even then, you can compress to a rate below the entropy of x or the entropy of y respectively. Okay, so let's see an example of what this actually means. So let's take the following source or following pair of sources where it's called the doubly symmetric binary source, and it's as follows. So xn is IID Bernoulli half. Yn, the marginal of yn is also Bernoulli half, but xn and yn are correlated. So the probability that xi equal to yi, it is 1 minus p over 2, and the probability that xi is different from yi is p over 2. Okay, so this is the doubly symmetric binary source with parameter p. It's for some p between 0 and 1. Okay, so what does this look like? Have you seen something similar before in some other context?
Bernoulli distribution.
It is Bernoulli distribution, yes, but
or symmetric binary symmetric.
Exactly. So you've seen this in the context of the BSc. It's as though you're generating x according to Bernoulli half and passing x through a BSCP to get y. Right? So, or likewise, since it's doubly symmetric, you can take y and then pass it through a BSCP to get x. right? So the marginals are still Bernoulli half, but jointly they are very correlated. Right? So it's as though you take X, pass it through a BSCP to get Y, or you take Y, pass it through a BSCP to get X. So these two distributions are identical. Right? So this is the so-called doubly symmetric binary source. Okay, so if we had to compress each of these separately, then what rate can you achieve? So what is h of x? So what is h of x equal to? So it's equal to 1, right? It's 1 bit. H of y is also 1 bit. So if you had to compress xn and yn separately, independently of each other, I mean, if you just had to use the standard, a standard optimal code, then basically you can't obtain any sort of compression. It's still 1 bit per symbol, so it's as good as not compressing x and y at all. Right? But on the other hand, if you look at this, so that would be these lines, right? H of x and h of y. So this corresponds to no compression. Now, but the green lines correspond to something much smaller, right? If p is small, then h of y given x and h of x given y could be much smaller. So what is h of y given x equal to? So what is h of y given x equal to for the doubly symmetric binary source?
So we can write h of x comma y minus hn.
Okay, but I mean, so I'm giving you the distribution, right? I've told you that the joint distribution is the following. What is out there? So what will h of y given x be equal to? It's not 1 minus h of p, but something close.
So P log P.
Sorry?
P log P. We're going to calculate
Is it
like
p
P of
log
x.
p? Check.
P of x.
h of y given x?
One minus p log p, sir.
1 minus p, sir. 1 minus p log 1 is. If we use this one, p of x value, sir.
So you're saying h of y given x is 1 minus p log 1 minus p?
No, sir. One minus p log p.
1 minus p log p. That's not correct.
Sir, is it like p log 2 by p?
No. So look, so you're obtaining y by passing x through a BSC P. Right? So what is h of y given x going to be equal to? So what is p of y given x of 0 given 0? P of 0 given 0.
One minus p, sir.
It's going to be 1 minus p. What is p of 1 given 0?
It should be p, sir.
P.
What is p of 0 given 1?
Again, it p, sir.
It p, sir.
1 minus p.
One minus p.
Okay, so using this, what is h of y given x?
Sir, is it 1 minus p log p by 1 by p by 2?
No.
So 2 times h of 1 minus p plus h of p.
2 times. Sorry?
H of 1 minus p plus h of p.
P plus H of P? No. How did you get this?
No, sir. No, I'm just. Okay, sir.
Yes. So it's not that hard to calculate, right?
But 2 times h2 of p.
Sorry?
2 times h2 of p. H2 of p.
Uh, your voice is not clear. Sorry. Two times H of P. How did you get that?
So using formula of entropy hy by x equal to p
So
of
what
y by
is so what is the formula for H of Y given X?
it's p of
Ah,
p of xy log p of xy by p of x, or p of
okay.
log p of xy by p of
Here
x,
is a negative sign here
p of xy by p of x.
by P of Y. Okay. So this is basically summation Y.
Some steps.
H of Y given X. So it should be P of X.
P of x this way.
P of Y given X. Right. So what is this equal to?
Okay, sir. Only means 2 times will not come. P of x will cancel 1 by 2. H2 of P.
Yes. So h of y given x and h of x given y, they'll both be just equal to h2 of p. So what is h of x comma y equal to?
One minus H2 of P.
1 minus h2 of p?
No, sir. That
1 plus H2 of
plus. There is plus.
That's 1 plus the binary entropy of p. Right? So now if yeah. So if you compress x and y separately without doing any sort of distributed source compression, essentially you can't achieve any compression. So h of x, the minimum rate at which you can compress x is 1 bit. The minimum rate at which you can compress y is 1 bit. But by decoding x and y jointly, even though x and y are encoded separately, if you're allowed to decode x and y jointly, then the claim is you can do much better. You can maybe do it at any rate close to these green lines. So this region, any point in the gray region is achievable. And so in particular, if p is very, very small, right? If p is very small, then h of y given x and h of x given y are also very, very small. But no matter how small p is, h of x and h of y are still 1 bit. So independently, if you had to encode and decode xn and yn independently, then really no compression is possible, essentially. But if you're allowed to jointly decode xn and yn, even though they're encoded separately, you can achieve a much, much smaller rate. So as you will let p to tend to 0, this green set of lines move towards the left, right? As p becomes smaller, the green lines move to the left, but the black lines remain where they are. So the more tightly they are correlated with respect to each other, there's a higher rate which you can achieve. Sorry, the rates that you can achieve are much, much lower. But this is, of course, assuming that you can decode xn and yn jointly. Okay. So in the next class, we'll see how to actually achieve these rates. Okay, and we'll give a proof. I'll give a proof of that statement. Okay, so we'll stop at this point. Are there any questions?
Sir, if we are reducing,
Sorry, Girish first.
sir, so what I was asking is, sir, if we reduce P, then and if we do decoding jointly, we can get
Yes.
better results. That is what the statement.
Correct. I mean, P is determined by the source, right? That's not in your control. The only thing in your control are the encoders and the decoders. But the only statement I'm making is that if xn and yn are very highly correlated with respect to each other, then it is possible to achieve much lower rates, or in other words, improve or get much better performance in terms of compression by decoding them jointly, even though they're encoded separately.
So, sir, means like since P is not in our control, how we can determine or how we can estimate or how we can go about?
How we can estimate? Well, that's generally given by the problem, right? So for example, let's say that you're making sensor measurements, then maybe you first estimate what the joint distribution is, because so the sensor measurements, I mean, typically like in standard communication setups, it is not always one-way communication, right? There's some exchange of, say, channel parameters or the model which is exchanged. So you can always perform some measurements and then share this data, estimate what the joint distribution is, and from then on, just use this joint distribution for compression.
Right.
Right? And even a rough estimate is generally good enough to. It's better to just first estimate a little and then do compression, because that will give you long-term savings. And even if you're off by a small amount, it generally doesn't matter in practice. You're still doing better than compressing them separately. I mean, sorry, by compressing and decompressing them separately. Okay, any other questions? Suman, you had a question?
Yes, like in the problem, like P of x comma 0 comma 0, whether that will be 1 minus p by 2, it is not 1 minus p by 2, right?
Sorry, P of 0 comma 0. So P of 0 comma 0 is 1 minus P divided by 2. I'm sorry, I didn't get what the question was.
So now while calculating,
I'm sorry, I think your voice just cut off. I didn't hear anything after when we are calculating. Maybe you can just type it if there's some audio issue.
to h of x comma y minus h of x.
Okay, I think we lost Suman. Are there any other questions? Okay, so if there are no further questions, then we can just stop at this point, and we meet in the next class.